This video is going to look at rates of change and the notation associated to rates of change. So when we're studying rates of change, two rates of change come to mind. So average rate of change and instantaneous rate of change. Now, conceptually they are very different, but mathematically they are closely related. And so we're going to talk about the mathematics associated to these as well. So average rate of change looks at the change of a dependent quantity. So dependent quantity we typically think of as x over a given interval. Okay, so we have to have a period of time or a period over which we're looking at the dependent quantity, so looking at x, and then the change that it produces in the independent variable, so we think of y. So in other words, how is y changing as x changes from this value to that value? And so when we compute it, we require 2 points on the function, so x1, and this is, if you want to think of this as y1, you can. x1, y1, and x2, y2. Okay, and then the average rate of change, I use AROC, is computed by, again, the change of the dependent quantity. So this is dependent. And then the denominator is the independent quantity. Okay, so sometimes you may have time, you may have other things going on. As you look at this formula, you may realize that, okay, this looks a lot like slope, and so that's actually very true. And I have a note down here. So computationally, the average rate of change is equivalent to computing a slope for a linear function. Okay, so if we have a linear function, we have to compute m, and it's going to be the same. However, when we're talking about the average rate of change, these typically deal with physical quantities in the world. Okay, so physical quantities such as population, height, weight, so physical quantities. Okay, and so when we have physical quantities, the interpretation becomes vital. And that interpretation follows something usually pretty similar to this. So on average, between the two observations for our independent variable, so x in this case, we say the function or whatever is changing per unit of x. And so I have a note here. This is a general format that we'd like to follow when we're talking about average rate of change. But if you have units and context, be sure to include that when you can. Okay, and so average rate of change, again, looks like slope. And the other rate of change, instantaneous rate of change, that one is actually a little bit harder to compute. Conceptually, it might be a little bit easier. So again, average rate of change is over an interval. Instantaneous rate of change, we note that it is at a specific value of the independent variable. So this is saying, for example, at x is equal to 3. If x is equal to 3, how is y changing? Okay, and we'll introduce notation to help us with that. But to compute instantaneous rate of change, at this point we don't have enough tools. Usually when you study derivatives, derivatives are actually allow you to compute this precisely. Okay, so right now we're just going to estimate it by making a sequence of average rate of change calculations where that quantity on the bottom, that interval, becomes smaller and smaller and smaller. Okay, so when we make that smaller, then we're going to get a more accurate idea of what the instantaneous rate of change is. Okay, so some notation that typically follows with all this is delta notation and prime notation. So delta notation, delta looks, at least a capital delta in the Greek alphabet, is a triangle. It looks like a triangle. And all it refers to is change or difference in a value. So if we're looking at independent quantities, so for example time, if t represents time, we would write delta t to represent the difference between t2 and t1. Now it could be reversed, doesn't much matter. And then similarly for a dependent quantity, you can define y of t similarly. So if we look at average rate of change, we would say that it's the change in y over the change in x. And adopting this to the formula that we had on the previous page, we still had delta x on the bottom, but the numerator we could write as delta f. Okay. And again, delta, all it means is change, so we have to have some time or some interval associated with all this. And so prime notation is the other type of notation. This is typically used when we're talking about instantaneous rate of change. So again, how fast it is changing at a specific moment, and is denoted by y prime. So if we look at a linear model, y is equal to mx plus b. Okay, m, really we could write that, so that is how fast it's changing, and that is constant. So we could actually write this, if we wanted to, as y is equal to y prime times x plus b. Okay, so at any specific moment, the slope, let me get back here. So the slope is equal to the instantaneous rate of change, so y prime. Okay, more on that to come. Alright, so just to summarize what we talked about, prime notation is used at exact time, typically with instantaneous rate of change, and delta notation is over a specific time period, so average rate of change. And then now to convert between the two, again, we were talking about an average rate of change if that interval gets increasingly small. So if that difference becomes 0 or approaches 0, we can actually estimate, we can use the average rate of change to estimate the instantaneous rate of change. So that's really what I'm saying here. So if delta t and then this symbol means much less than. Okay, so if they're pretty close, then we can actually say, okay, well, the delta notation, so the difference in a time period can actually approximate the change at a specific moment. Okay, and then if you meet this condition, so this is a necessary condition, you have to satisfy this condition first, then we can actually use the average rate of change to approximate the instantaneous rate of change. So what we're saying, okay, average rate of change is this formula, but if we look at it in delta notation, we say delta y over delta t is approximately equal to y prime, and then that's more or less an equation for us, so we can rearrange, multiply by delta t, and we get this. Note for a linear equation, we can write this as y minus y1 is equal to y prime t minus t1, and that actually is point slope form of a line. Okay, and then again, on a linear relationship, or when you have a linear relationship or you're working with a linear model, you actually get true equality, and then that's where, again, you kind of get that point slope form, and you can rearrange it. You can rearrange this and get y is equal to y prime times t minus t1 plus y1, and then go through some algebra, and you could rewrite this. You'd have to rename some stuff, but you would get y prime times t plus b, which is your slope intercept form. And then you get a linear model out of it.